Hello, everyone, and welcome back to your channel of probability and statistics. Or basically, I placed it in the channel of basic engineering. But we were talking about constructing confidence intervals for the mean and the variance in the previous sessions. Today, we are going to look at the other side of the coin, something called the test of hypothesis or hypothesis testing. Test of hypotheses. So what is that? Remember we said that in real life, everything is probabilistic. You cannot know it for sure. So suppose you are a customer or you are a producer, but you are getting your raw material like parts from some supplier. And this supplier is presenting you with, let's say, if you are, say, a builder and you are getting, you know, rebars, like steel bars. And the claim is that these steel bars have a specific strength. So you will select a random sample from your supplier, run, say, a tensile strength, a stress test, and see where these bars break. At what stress do they break? And you can average them and see. Of course, the average will not be exactly the same number as what the supplier is claiming. So you want to make a conclusion. Should I accept the lot that they are sending me, or should I reject it? Okay, so the idea here is to either accept or reject. In fact, we don't say accept, but we are going to talk about that in a little while. Sometimes you are, say, installing doors in a door frame. You don't want the doors to be smaller than the frame, of course, and you don't want them to be bigger than the frame, so they won't fit. So in that case, you want it to be exactly some number. Notice in the first case, you want it to be as high as possible. In some other instances, you want it to be as no more than something, so or no less than something, no more than something, or exactly something. So we have three flavors of these tests. Usually, well, traditionally in statistics, we go through few steps. I will talk about them in a second. Uh, and then we'll take examples to, make it clearer. The first step we take is that we set the null hypothesis. Okay? Null hypothesis. And it's always going to be equal, like mu, if we are testing the mean. Okay, we'll start with testing the means. Mu equals some numbers, let's call it mu sub 0. The null hypothesis always comes as an equality. Mu equals something. I know that in some management textbooks, you may see it says mu is greater than or equal to mu 0, or mu equals mu 0, or mu less than or equal to mu 0. But statistically speaking, mathematically, the null hypothesis has always to be written as mu equals something, equal a value. Okay? Now, then we set, and just we call it that null hypothesis. H stands for hypothesis, and the null is what we are having as a claim. Okay. Then we set what we call the alternative hypothesis. We call that H sub 1. If that's a 0, that's a 1, right? Some people use the letter A for alternative. That's fine. But in these sessions, we are going to use H sub 1 as the alternative hypothesis. The alternative hypothesis comes in three flavors. I can say mu is less than mu sub 0, or mu does not equal mu sub 0, or mu is greater than mu sub 0. So if mu is less than mu sub 0, it means that the null hypothesis mu is greater than or equal, right? If this is less, then this is greater than or equal. If this is not equal, then that's strictly equal. And if that's greater than, this would be less than or equal. So we know what type of null hypothesis by looking at the alternative hypothesis. Okay? Bear with me until we are done. Step number 3 is obsolete. We don't use it anymore. Okay, so I'm going to write it in a different color. Set level of significance. Well, we can still do that. Level of significance, remember the alpha we used in constructing the confidence interval? It's the same alpha. We'll talk again about it in more detail. Alpha. So you can say alpha is 1%, alpha is 5%, alpha is 10%, whatever the case might be. Step number 4, set the test statistic. What is the test statistic? Well, if we are testing mu and we know sigma, which I have no clue how, we would use the z. If we don't know sigma, but the sample size is large, we still can use the z. If we don't know sigma and the sample size is not large, but we know that the distribution is normal, we use the t. In these sessions, I will always use the t. I don't like using the z. I think it's very like theoretical, right? So we are going to set our t, and we say the t statistic equals, we already know, x bar minus is expected value, which is mu, divided by its standard error, which is s over square root of n. Okay? Step number 5, we are going to set the rejection region. Rejection region or regions. If mu is less than mu sub 0, my rejection region would be something like that, and this is alpha. Again, this I should have done it in blue because in brown because we don't use it. I'm just explaining to you in the past what we were doing. If its mu doesn't equal mu sub 0, meaning if it's more I reject, if it's less I reject, so this is alpha over 2, this is alpha over 2. And finally, if mu is greater than mu sub 0, we reject the whole alpha is on the right. So whether it's to the left or to the right depends on the alternative hypotheses. Okay, and of course, based on the number of degrees of freedom, I know that I can find this value, T1 minus alpha and degrees of freedom. These are T alpha over 2 degrees of freedom and T1 minus alpha over 2 degrees of freedom. Here it's T alpha degrees of freedom. So we can set these values. That was in the past. Don't worry about it. I just wrote it here. So in fact, 3 is, we usually have to set it, right? So assume this is blue and this is brown. Notice that in the first 4 or 5 steps, we haven't yet performed any test. We are just setting the stage. We are saying, this is what I'm going to do. This is the statistic I'm going to use. And based on that, I either reject the null hypothesis in one of these 3 cases. But again, as I said, excuse me, we are not going to worry about that. And I will explain why we stopped saying the rejection region. But sometimes they may ask you, that's why I drew it. But if you are running a test, we usually don't set this. Step number 6 is that now I'm going to select a random sample from the producer's claim. They claim that, these doors are set to a specific width, whatever it is, 80 centimeters, whatever the case is. So I'm going to measure the width of each one and find X bar and find S and do whatever. So I'm going to calculate T. So T calculated, let's write it like that. It's already what we are saying here. So it's going to be X bar minus this guy right here, mu sub 0 comes here. So if I want this to be 80, I'm going to say X bar minus 80. It doesn't matter which alternative hypothesis I'm using. I'm always going to get this number from the null hypothesis. It's like a law. You always get it like that. And then you divide by S that you calculated here. You calculated X bar and S over the square root of n. In the old days, I would see this number. If I'm using this alternative hypothesis and this value falls here, I will fail to reject. If it fails on the line, of course, it will never be on the line, but mathematically speaking or theoretically speaking, if it's on the line or to its left, I'm going to reject. Here, I'm going to reject either if it's on this line or to its right, or on that line and to its left. And here, I'm going to reject if it falls right on the line or to its right. Later on, we said, if you are going to give me one word and say reject, and we don't say accept, we say fail to reject or fail to reject, I wouldn't know, does the t value when you rejected, was it here? So I can say, you know what? It's very close to the acceptance region. So I may run another test or I may accept it. Or does it fall here? Oh, way into rejection region. I definitely would reject. This doesn't tell me that. This number doesn't tell me that. All what it tells me, it falls into the rejection region or not. So instead of that, we use what we call the p-value. We are going to talk about that. So today is a very theoretical session, but just to set the stage for what's coming. Find the p-value. We'll talk about that. So in numbers, after you calculate that, maybe the seventh step is the conclusion. If the p-value is less than or equal to alpha, reject h sub 0, and you have to say, if I reject it, at what level of significance I'm rejecting it. Am I rejecting it at 5% or at 1% or at 10%? So you say reject the null hypothesis at alpha level of significance. If the p-value is greater than alpha, and we have to write this in our report, so you will say, okay, I got a p-value of 0.2, okay, which is much higher than 0.05, or I got 0.04, which is slightly less than alpha if alpha is 5%. So you say that. We don't say accept, we say fail to reject h sub 0 at alpha level of significance. So that's everything we are going to do. The first steps are easy. Usually they are given to you in the problem. They tell you check to see if mu equals that, or if it's greater or less or doesn't equal. We want to run it at alpha equals 0.05. You know this is already written, and based on that, forget about step number 5. So all of this is given to you in the problem. So your job is to calculate the t and then find the p-value and see how we do that. And based on that, you either reject or fail to reject. Very simple. Okay, now we are going to say, if I get a sample and I reject it, I may take another sample from the same guy and get it and get the answer here. So I would fail to reject. It's like it's not really, I have to always um, live with uncertainty. I'm not sure. Did I make a good choice? Did I reject it? Did I was um did I make the right choice of rejecting it or failing to reject? Because if I fail to reject it, mean I would accept the lot, right? So, oh my God, was that the right decision or not the right decision? That's why you always would have this in the back of your mind when you make a decision. And that's why uh, many, many people, instead of just doing it like that, it's too soon, I think, to talk about that, but I would ask you as the client. You said you wanted really to have the value at say 80 centimeters. But just tell me, what values, what range of values would you be willing to accept? Like 79 is okay, or 79 and a half, or 80.2, or 80. So give me some range, and that would help me figure out, that I set the stage on how to accept or reject. Again, this is very soon. We are going to talk about that in more detail. But now I want to show you something that when you make a decision, whatever the decision is made, you may be having one of two types of errors. What do you mean? Remember, I said you can never guarantee that the decision you are making is right or wrong. We only have a probability of talking about that with probabilities, meaning, let's say I'm going to say here, my null hypothesis, even though we don't know, but my null hypothesis, it's either true or false, right? Cannot be anything else. And your decision is either, even though it's failed to reject, we are going to call it accept with a grain of salt here, or reject. Okay? So if it's true and you fail to reject it, that's good, right? Because it was true and you accepted it. But if it's true and you rejected it, can you tell me what is the probability that this happens? So it's a true, meaning it is above this line or between these two lines or to the left of that line. But the guy was unfortunate, and when you picked the sample, it fell into the rejection region, so you rejected that. What is the probability that you would commit this type of error? Do you see that the rejection region is alpha? So the guy was unfortunate that the point or the sample statistic fell into the rejection region that has an area of alpha. So that is alpha. Meaning, if it's true and you accepted it, it must have been here that has an area of 1 minus alpha. Of course, this row has to always add up to 1. It's either you reject or accept, right? There is nothing else. But what if it's false and you rejected it? That's good. But what if it's false and you fail to reject that. We'll talk about that more because that's a little tricky. But since we call this alpha, we are going to call this error probability beta. And sure enough, if you reject a false, then the area would be 1 minus beta. Okay, we call alpha, remember, alpha was called the level of significance. It has three names, right? It's like, okay, it's very enigmatic. I mean, so you can call it the level of significance, or we call it the type 1 error probability. So alpha is type 1, beta is type 2. And it has a third name, usually in management, or we use it, or psychology sometimes, or in fact, you may have four names for it. We call it the producer's risk. Why? Because the guy was really having the null hypothesis true, but he was unlucky when you selected a sample of their production, it failed the test. So even though he was saying the truth, unfortunately, he failed the test. So that's the risk the producer is taking. Also, usually in medicine or psychology, we call that the false positive. See how many names? So you can hear that one of these four names and all of them refer to alpha. Okay? 1 minus alpha doesn't have a name, unfortunately. It's like the nobody likes it. Likes 1 minus alpha, so it doesn't have a name. But what about beta? Beta is the type 2 error probability. It's the consumer's risk because you may fail. So I'm sorry, you may accept a false hypothesis. Okay? It's false. The producer is not telling the truth, but you were unlucky. The sample statistic didn't fall into the rejection region, so you failed to reject it, which means you accepted it. So it's the consumer's risk. And of course, we can call it false negative. On the other hand, 1 minus beta is called the power of the test. We'll talk about beta and 1 minus beta later, but alpha and beta, one of them is a producer's risk, one of them is the consumer's risk. And that's why we try to set a balance so that one of them will not be much larger than the other. Okay? Again, beta is a little tricky. We are not going, remember when I told you, if you ask your client, what really do you accept? Okay, so you say, okay, I want the strength of this material to be above, say, 1,000 psi. But if it's 990, does it really matter, or 995, or where do you want to draw the line? Once they draw the line, we can calculate beta, but without that, I don't know. There is no such, doesn't have a meaning. So if I increase alpha to increase the producer's risk, I'm reducing beta, which is the consumer's risk. And if I increase beta, I decrease alpha. You cannot decrease them both except you pay the price. And what price do you pay? Sample size. You enlarge the sample size. That's the only way you can reduce both of them. But this is basically, we are setting the stage for the test of hypotheses of the mean of one population. Okay, mu. I'm not going to go any further now. I hope you understood what we said. Again, if you didn't understand exactly beta, that's fine. If you didn't understand because we didn't talk about finding the p-value, I'm going to talk about the p-value now and then I will stop. So what do we mean by the p-value? Suppose here I may get a value of my statistic here, which I will reject, or I get it here, which I fail to reject. And let's make some examples here. Okay, the p-value. I'm going to illustrate it completely differently from the point of view of statistics or mathematics, but in regular English language. I'm going to say, what is the best, I would say the 100th percentile? What is the best outcome that comes from here, theoretically speaking? I want it to be higher than this line. Yeah, at infinity. It will never be infinite, but if the statistic is infinite, that's the 100th percentile, right? If it's here, it's the 90th percentile, 80th, 70th, 60th, 50th percentile exactly in the middle, 40th, 30th, 20th, alpha percent. So I'm saying if I want to rank your statistic, what would be its percentile? That's the p-value. So the p-value here may be, for example, the first percentile, right? It's like 99% of the distribution is better than that. So the p-value here would be the cumulative of this point. It's the area from negative infinity up to your statistic. Okay? And of course, if it's less than that, it's bad, so I'm going to reject it. Let's move to the one on the right. If I don't want it to be higher than that, what is the best what is the 100th percentile? The 100th percentile is at negative infinity. And as I get closer, the percentile decreases, decreases, decreases. It becomes 50th here, 40th, 30th. Oh, for example, it's 30%. That's the area to the right of your statistic. And since this area is greater than alpha, you will not reject. And that percentile is the p-value. So here I measure from the left, here I measure from the right. You learn that to find the area to the right of a number is the same as the area to the left of its negative. So if this is the t, and that would be the negative t since the mean is 0, and this area also, I could measure the area to the negative t, and that would be the p-value. The tricky part is that you want it to be exactly 80. If it's more, it won't fit in the frame. If it's less, you will get air and noise and dirt coming through the door. So where is the 100th percentile? Exactly in the middle. If I go slightly to the right or slightly to the left, my percentile would decrease. Do you see that if I come here, if this is my statistic, the negative t and the positive t, the area to the left of that is worse than my statistic, and the area to the right of that is also worse than my statistic. So my p-value is the sum of these two areas, or twice this area. Or twice that area if you wish, but it's easier to calculate the cumulative of negative t and then multiply it by 2. I think this makes more sense to you to understand, is that where is the best? Is it in the middle? Is it to the left? Is it to the right? And where does my sample statistic fall? Or where does it fall? Okay, so is it better than the worst alpha percent that I will reject, or it's worse than the worst alpha percent? And that's what we are going to do. And it's really very easy how to calculate this area or this area multiplied by 2 or that area by looking at the negative of t. So I'm going to stop here, and in the next session, we are going to solve a couple of examples on uh, a test of hypotheses. One in which I will give you the sample values, and in the other, I will give you just this, give you the X bar and S right away, and see how we can solve them using your TI, for example, and that would be it. Okay? I hope it wasn't tough enough. This one, and I wish you all the best and hope to see you soon.